So welcome everybody. Today is the fifth webinar that we're running through the WaterSense consortium, which is a European funded research and action project that we're working to, where the University of Sydney is working together with a group of companies in Europe and one in Australia. And this is a fifth seminar where particularly we have Pedro, who is from Hidromod in Lisbon, who is going to give us a talk on crop detection, and then Joost Brombacher, who's from ELIF in the Netherlands in Wageningen, and he is going to give us a talk about his automated irrigation detection that they've been developing. So I'll straight away hand over to Pedro. We'll do about 20 minutes, and then we'll have 5 minutes or 10 minutes for questions, and then we'll switch over. But it runs for about an hour and a half, so if there are more questions, we might defer to after Joost's talk. Pedro, over to you.
Thank you very much. So I think you can see my screen now. Okay, então, very good morning here for you. I will be talking to you about crop detection. My name is Pedro Chambel Leitão. As William said, we are based here in Lisbon, Portugal. And I like to start by showing this slide, well, to let you know where me and the company and the university where I came from, the kind of, well, a little bit of our history, what we do. And so we are into numerical modeling. And it all started in the 80s, where MOID, this modelo hidrodynamic in Portuguese, which means hydrodynamic model, and so it started with a PhD. Everything starts with a PhD, and the group where I came from the University of Lisbon, was started, and then in the 90s, Hydromod, which was a spin-off from this group, was born. MOID started to be used for consultancy, and later on in the 2000s, it's when I joined the group, when I joined this story that you are seeing here, when the MOID started being used for inland waters, and so I started by developing the first version, which was just the objective of my first year was to develop a 1 cubic meter hydrodynamic model based on all the generic concepts of that MOID had at the time. And from then on, MOID start to be what you have there on the right, which is a watershed model that does not only simulate the soil, but also the river, the runoff, everything that you need to simulate to have the water cycle. Later on, AquaSafe was born. AquaSafe is a system that allows us to make these models operational, and in fact is not only MOID, and here MOID is the model on our heart, our numerical model, but of course we are interested about and we are running many other stuff. And this AquaSafe is what allows us to deliver operational services based on models and measurements and remote sensing and everything to our clients. Then again, in the 2010s, Aquafarm and WaterSense were two projects that we have running, that we started running at the time, and that allow us to start delivering services to clients interested on managing water at the inland waters. And of course, and there is other other aspects like this MOID land being adopted by Bentley to as their numerical modeling engine. And okay, so I would say that with this you have more or less an idea of what we are working on. Physical modeling of water, and of course everything associated, namely also plant growth and everything that is important for the water cycle. Okay, going to the remote crop detection that appeared here as a way for us to improve our numerical modeling. just a small slide. I just got some stuff from the internet, but mostly from the United States on the remote crop detection. So the beginnings was this Landsat 1 that at the time it was not, for the first time was not called Landsat 1, but eventually it was called Landsat 1. It was deployed on 1972, and based on this satellite they started this group that is mentioned there, this resource inventory service through aerospace remote sensing, where they started, let's say, trying, they made the basis on the crop detection. So this is quite old stuff from the time that people had mustaches, as you can see there on the right on the image. And they have these typewriters that look like computers, or the other way around. And so this slide is just to tell you that this started a long time ago, and with this Landsat, which still nowadays is a program that goes on by the Americans. In fact, in this picture, it's not Landsat 9 there, but this is just to show you that Landsat dominated most of this for a long time. And then, and this is the part where the Europeans start to try to keep up, where the Sentinel satellites start to be start on operational, Sentinel-1 and Sentinel-2. Since then, since the Americans started this, presently we have many world crop monitoring systems from FAO, from this US Agency for International Development, this China Crop Watch, and you also have this MARS, this Monitoring Agriculture with Remote Sensing from the European Commission. You have GeoGLAM, you have NASA Harvest Mission. So just to mention some of the world crop monitoring systems that still nowadays are working for different purposes. Okay, in the meantime, and again, don't forget that I'm talking about in the perspective of a numerical modeler. And so we got into this as a help for us. We ESA made an effort of developing an open source algorithm to help us with this crop detection. So this ESA Sen2Agri software was developed. You can look it up in the internet. It is free to use, open source, and this system is an operational standalone processing chain, which is using Sentinel-2 and Landsat time series, and it produces many different stuff that are mentioned there, mostly related with cleaning up the images, and in the end producing statistics, and with that running some random forest algorithms to get the cultivated the crop maps. For a guy like me, this was a very interesting project, because it allowed us to get into understanding the best the problems, and and to understand some algorithms to be able to apply this into our daily work. Sorry. Then after this, ESA also financed another project, which was the Sen4CAP, which is based on the Sen2Agri. And this is, again, it's another project, but still it has a tool. Though it was based on Sen2Agri, it's let's say a standalone tool, which was developed based on Sen2Agri. And the big difference is that it was also using Sentinel-1, which is radar, in opposition to Sentinel-2 and Landsat 8, which are optical. which main advantage of Sentinel-1 is that it does not have any interference from the cloud. And again, it produces markers and statistics based on these images, and based on this, it produces per parcel, and this is another big difference with Sentinel Cent2Agri, is that it makes the crop detection parcel by parcel, so you have to provide them the parcels. And so when the statistics are generated, again, a random forest classifier is applied to the parcels, and based on this, the part, and I forgot to tell, this software was developed with a very clear aim, which is here, as on Europe, as you know, you cannot do any agriculture without getting some money from the state, and so all this is very controlled, and so we have this CAP, which is this European agricultural common policy, and so this was developed to allow the states to control their farmers. So basically, here in Portugal, until let's say until June, all the farmers have to go to a place where they say in each one of their parcels what is the crop that they have there, and then this has to be controlled. And so this software was developed to take advantage of all these declarations, use this information of the declaration of the farmers as training information for the crop detection, and also so it uses part of the sample to train. They know that the training sample could have some errors, but still is a reasonable enough training sample, and then they check the other parcels to see how likely it is that the parcel is well declared. If the kind of crop that was declared, if it is, how likely it is to be right or wrong. And if they have some information that it could be wrong, what they do is that they make a warning, and the farmers get a warning that maybe they have to check, to send them some photographs to prove that the crop they declared is there. Okay. Well, in the meantime, so we start, well, from the beginnings of this project, we were accompanying in this, and in the end, well, from all these efforts, we were looking to get some crop detection capacities for numerical modeling, but in the end, we end up also producing and helping our national paying institute of these subsidies for them to allow them to have a crop detection system. So nowadays we are in fact controlling the 4 million parcels that we have in Portugal. So Portugal is this area here, if you never looked at it. So it's this this area covered by this Sentinel-2 tiles, and here on the right is our islands, also covered by this Sentinel tiles. And so we are controlling all the 4 million parcels and providing this service to our paying agency. And it is being used still, and this started just last year. It was being tested for rice and tomato. And so the farmers were really receiving notifications, and there was a mobile phone app where they would have to take the pictures to prove that in fact a parcel that was marked as maybe it's not the crop was not well declared. The farmers would have to take the pictures with their mobile phones to prove that it was. Okay, now getting to Australia. In WaterSense, and in fact in our work that we have been doing, this crop detection is quite useful for us to have an educated guess on the kind of modeling results we are having, and also as an input to our modeling results. So we start also trying to use this to classify the land use in the Namoi watershed that we are studying in Australia. And so you can see there on the left top, you can see here the crop map. You can see here on the bottom, well, the F scores that we were getting, so values closer to 1 means better results, lower values mean worse results. And so this, in fact, is ongoing work. And you can see there on the right, for example, one of the works is to try to filter out some of the noise that the NDVI have. And NDVI is one of the key elements of this detection. So basically, you can see here the phenologic evolution of the plant, and this peaks down. They basically mean that there were some clouds or there was some confusion on the information. On the bottom, you can see already the smoothing of these curves. So now an example for our study area. So you can see here some parcels that were, let's say, declared as cotton. And as you can see here on the left, so you have all these lines. You can see, well, these ups and downs. And you can see that if you know the cotton is something that happens around this area here, and and there are some lines. For example, the one which is very clear is this one. So this was clearly not cotton happening this year, and you can see that some others also do not seem like they are cotton for sure. And we know this, and we can also know this by just trying to figure out what is the start and end of the growing season. So these points here, you can see it's we have an algorithm to detect the maximum stage of the development of the plant, and down here the beginning, the seeding, and here the sowing. Okay, so basically what we are representing here in this square is the phenological development of cotton, and by knowing this, we can and what you can see from the left graph to the right graph is that the lines where we were not able to detect any reasonable beginning or end of the crop at this period, which is normal to have cotton in Australia, then we will remove it. And so this also is a filtering activity that allows us to have a nice training sample for the crop detection. Okay, here to show you some other examples of the kind of crops that we detected there. So you can see barley, which is centered here. You can see chickpeas here. You can see some wheat here, and for you maybe this is all more or less obvious, but not necessarily to me, which I am just opposite from you in the world, and the seasons are a little bit different, so none of this is obvious to me. And for corn, so we have the corn in this time of the year, and we have the faba beans, we have canola, and here other summer crops. Of course, there is a bunch of possibilities. Okay, for what in WaterSense? WaterSense is about helping the farmers with managing water, and crop type classification is very important for us to go from the NDVI to KC. KC basically it's the oldest form of calculating the water needs in the plant, and it allows you by just having some climate factors calculating the what is called reference evapotranspiration, and by multiplying with this KC and some other factors, you can get what is the cultural evapotranspiration. And this allows us to use this together with other information on soil and other stuff to have information on water budget at the parcel scale, and to deliver this information into the final clients. Okay, this is just to give you an just for you to see the final word. This one of the important inputs, which is soil. We got some soil information from the NAMOI, the area of study. So you can see here the parcels, and you can see here the soil properties, which are quite important because they give them for example, this available water content, which is basically the water that is available for the plants to evapotranspirate for each one of the soils, and also the saturated conductivity, which will determine the amount of water that is lost by percolation. Well, and all this, knowing the KCs, knowing the NDVIs, knowing soil properties, you can get maps like this, where you have the amount of water available in the soil at a certain point, and you can see here the blue higher content and the red lower content, and you can see here on the right the volumes of water, in this case per month. And because we have the crop detection capacity, we can also show this by crop. Normally, it's a sensitive issue for you to show by crop, because you are the guys that are growing that crop might not like that you show that they are the biggest consumers of water, and so it's a sensitive result to show. Anyhow, you can for your final clients have all this different information: actual evapotranspiration, runoff, and percolation, which is relevant for you to know how much water is effectively being used. Okay, so still the biggest research challenges that we have to meet with all this, and this is some traditional slides here in WaterSense, is that we have two major challenges. One is to try to get information on remote sensing to be able to understand, for example, the evapotranspiration that is the major loss from agriculture in terms of water, and also merging all this information in time and space, and to get all this bunch of information in a usable way for the farmers. And of course, all these two challenges can be, let's say, divided in many other challenges that we have that are related with knowing if how we should use the local data, if the data is there available or not. Sometimes this is a gray reality. Sometimes it's available, sometimes it's not available. Sometimes you have it for historical, but you don't have it in a daily basis. And you also sometimes have to deal with forecasts, and so you have to connect what is the incast with the forecast. And so all, and of course, the different definitions that in which you have the information with different resolutions. So all this gives us, and this is our challenge here, the possibility in this project to try to, with real users, try to make this as useful as possible in the nowcasting and forecasting, because this is for what it matters for the business, is how our capacities of nowcasting and forecasting allow us to understand how the business can get more profitable, either by identifying lost water or by trying to predict what will happen. Yeah, and to make sure that we take the most out of all this bunch of data that we are measuring and getting with satellites and models and all this. Okay, so this is crop detection in perspective of a medical modeler, and with this I finish.